More training data may help with overfitting. Here we use the learning curve to see if more data really helps. So what does it do? Basically, it runs cross-validation with k-folds and then plots the average tuning error against the tuning sides. Also plots the average cross-validation error against the tuning sides. Now let's take a look at the tuning error and also cross-validation error regarding the size of the tuning set. For the small size of the tuning set, the tuning error is also small. However, it increases as the tuning size increases because we have more data points, and more data points would mean more error. Cross-validation error is large for small tuning size, but it increases as the tuning size increases because the model sees more training data and trains with more data. Now we take a look at specific cases to see if more data helps. In the case of a high bias model, this would mean we have a simple model. The training error is small with small training size increases as the training size increases and get close to cross-validation error. How about cross-validation error? As the model is simple, so it underfits. So more data doesn't help. Generalization error doesn't decrease as the training size increases. So our conclusion is that with a high bias model, more training data doesn't help. How about the case of high variance model? In this case, we have a complex model. Let's take a look at the training error and the cross-validation error to see how they look like. The training error is small with small training size and then increases slowly as the training size increases. The cross-validation error, or also the same thing, generalization error, is large, but then decreased as the training size increases. We could see the big difference between the generalization error and training error, and that difference decreases with more training data. So our conclusion is that with the case of high variance, more training data would help. There are other approaches for avoiding overfitting also. If we set a limit on the training time or some other stopping criteria, the model would be simpler, so would not overfit. This is called the early stopping approach. Another way is to have fewer features. The idea is that less irrelevant data would mean less opportunity to train the model with noise. So this would fix overfitting. Or we may have more features for fixing underfitting because it would make the model less simple. This approach is called feature selection. Another approach is to reduce the number of dimensions. We may transform features in high-dimensional space to a new space using, for example, principal component analysis and retain dimensions with highest variance such that the total variance would meet some criteria. For example, 90 or 95 or 98, 99% of the total variance. Another approach is to use independent component analysis that transforms the data set into another space in which dimensions are statistically independent, and then select a number of dimensions. Finally, we can use ensemble method. In ensemble method, we combine many simple models called weak learners. And aggregate predictions to create the final prediction. So this way, SML models are robust for avoiding overfitting, and they generalize very well.